So here, so some of students ask this question: why writing to X in P2 override Y in other C file? The reason is when you allocate these global data in this data segment, they allocate sequentially, contiguously. So for 32-bit processors, so the first X occupy 4 bytes and the second X occupy 4 bytes. Okay, X and Y. And because this is weak symbol, the linker choose this definition for the reference to X in this code. Okay? So in this code, because this can be written by another person, okay? The write to X, here he assumed he write to this double floating point number, which is 8-byte number. So if you do a write to X here, it's writing 8-byte data into the location X, which is referring to this location. And if you write 8 bytes, it will override X, not only X, but also Y, because they occupy contiguous space in the memory. Okay? So if you write to X in P2, it will override Y, definitely, in this code. Okay? So I think this should clarify the question. Okay, so what is symbols? Symbol is the lexical entities. Lexical, you can remind the lexical analysis phase of the compiler. Okay, so compiler first phase will be lexical analysis, and then syntax analysis, and then semantics analysis, and so on. So in the lexical analysis, it generates a series of tokens. So it identifies whether this is a identifier or an operator or a keyword, okay, and so on, or number. So symbols are just lexical entities. It's kind of tokens, okay. Usually the symbols here reference functions or variables. So you can have some function symbol or variable symbol. It's some kind of identifier, but it doesn't know whether it can be a symbol or it can be also variable. It can be a variable or a function. Okay, it depends. Okay, and each symbol has a value. Typically, to the linker, the value should be the address of the symbol. So for the function symbol, it will be the address of the instruction, of the first instruction of the function. The variable symbol, the value should be the address of that variable, the location. Okay? And the code contains definition and reference. So definition and reference means these are the definition and these are the reference. Okay? And the reference can be either local or external. Local means these are the local definition, which means this symbol is defined by this file locally. And some of the symbols, like this, are not defined here. So should be defined externally, and this is external symbol. And this is also local symbol, this is external symbol, and so on. Okay? So we are looking at this example. So this is a definition of local symbol, E. And this is a reference to an external symbol, A. And reference to an external symbol, exit, which is usually defined in this shared object, this runtime library. Okay? So this is actually defined in the standard C library. This is a definition of local symbol. This is a reference to an external symbol defined in another file. definition of local symbol x and y, and definition of local symbol a, and reference to a local symbol e, p, x, and y, and so on. Okay? Okay, so symbol is dealing with all global variables or static variables. And symbol is not variable. Symbol is can be a variable or a function. Okay? And it's kind of lexical entity that linker is interested in. Okay? Let's look at relocation information generated by the compiler. So by compiling m.c, this code, it generates this kind of object file. This is a binary file, but this is not an executable. This is partial binary file. Okay? It does not contain all the functions and all the data, so it cannot be executable, but it's a binary, it's a translated code. So this is the disassembled assembly code for this file. So it should go to the data section because this is initialized global variable, and this code should go to the text section. Okay, and this is actually x86 binary, IA32 binaries. So here, the first instruction is only a single byte. So this is CISC language, CISC machine instruction set. So the instructions are variable size. The second instruction is 2 bytes and so on. Okay, so this should be, this is a frame pointer, maybe push frame pointer onto the stack and copy a stack pointer to frame pointer so that it allocates new stack frame and so on. Okay, to execute this function, and it's calling function A. Okay, so it calls function A, and this is relocation information. It's calling function A, and it says this address starts at address 4 of this text segment, and they are using PC relative addressing. PC relative addressing. And it's calling function A, procedure A or symbol A. And address is unknown. They just use PC relative addressing. After calling function A, when it returns, it's doing some push operation, and it's calling another function exit, which is also they use PC relative addressing, and this. So this address, this 4-byte address, needs to be modified by the linker after the relocation, after they merge all the text segments, and they just put some number. So instead of 0, it's actually -4, because this is the most significant byte, and this is the least significant byte. So -4 is just to help their calculation. So you can assume this is something like 0. Okay? So this is just some kind of constant to adjust their PC relative computation. Okay? And this code should go to the data segment, and the relative offset should be 0. Okay? And there is a 4-byte. So this is first byte, second byte, third byte, fourth byte, and they are storing 7. So this is MSB, this is LSB. So least significant byte they store into the first byte. So this is actually little endian. Little endian, if you remember correctly, when you store data into a memory address, let's say you are storing 4 bytes of data into a memory, you can put lower byte to lower address and second byte to second address and so on. That's called little endian. The other way around is called big endian. They put MSB, most significant byte, to a lower address and so on, the other order. And they put least significant byte into location 0. Okay? So this is corresponding to little endian, which shows that x86 instruction set architecture use little endian for memory ordering. So you have to read, if you read this hexadecimal 00000007, which corresponds to 7 in decimal. Okay? Okay. So this is the data segment. So this is relative position in this segment, and you have 15 bytes of actually 16 bytes of main code in a text segment, and these two addresses are unknown because they don't know where is this function A is located or where this exit function is located. After they merge all the text segments together, their absolute position is determined. Then they can fix this address. Okay? So this relocation information just tells that starting at offset 4, this 4 byte address should be 4 byte, you have to change after relocation. And this address you need to change using PC relative addressing. That's all what it says. Okay? So this is the translated information for M.O. Let's look at A.O. So you have this definition and the function definition. So this goes to the text segment and this goes to the data segment, which is shown in the next. 잠깐만. 네, 여보세요? 저 수업 중이에요. My mom is calling me. She's still asking, so I just okay. Okay. So this code corresponds to this function, this procedure, a function definition. Okay. So it's also doing some pushing stack pointer, frame pointer to the stack frame, and then this is this move L is like a load instruction. From this address, it copies the data in this address into this register. Okay? So instead of load or store, they use move instruction. Okay? Because it's not load store architecture. RISC processors are based on load store, which means to do the computation, you have to load the data and do the computation. But for CISC architectures, you can move data from memory to a register, register to memory like RISC processors. But unlike RISC processors, they can do computation on the data in the memory. Okay? So the example, we can find some example here. Okay? So it's trying to load from memory address, it's trying to load into this EDX register. And this address is unknown. This address should be the EP. The address of EP is unknown, so, and they are using absolute address instead of PC relative addressing. Okay? So this just relocation information means that offset 3, you have a 4 byte address, and using the absolute address, you need to modify this address. This is unknown. Okay? That's what it said. and you should look for the location of this symbol after the linking. Okay? That's what this relocation information it says. And here the next instruction is also moving X into this register. The address of X is unknown, so they also use this mark. You should use absolute address. From this address, you need to modify and copy into this register, EAX. And then they move stack pointer to frame pointer, and then they do an addition. So this means using the address. So we are using EP, using the data in here as an address. So memory data pointed by this address. Okay? So you fetch a word from memory pointed by EDX and add to EAX. So this corresponds to star EP plus X. Because X is already loaded into this EAX, address of EP is loaded into EDX. Okay? So using the address EP, you access memory. So this corresponds to star EP and add the data to X. Okay? So this corresponds to star EP plus X. Okay? So, so you can do memory data plus register in this example. So this is actually an example of CISC instruction. You can do an addition, and the input can be one input are in the register, the other input is in the memory. Okay? And memory address is already copied into EDX by previous instruction, this instruction. Okay? So you are doing star EP plus X. And they manipulate stack pointer, and then they add Y to EAX, and the address of Y is unknown, so they also use absolute address. You need to modify this. So this corresponds to star EP plus X plus Y, and then they pop the frame pointer and then return. Okay? Return. Okay? So this is, you may be confused because you don't know the x86 instruction set. Okay? But what this relocation information set is, it just mentioned these three addresses should be changed after the linking, after the relocation. And these 4 bytes, so starting at offset 3, starting at offset 8, and starting at offset 14, is ask the linker to change this address using absolute address. And the address should be the address of EP, and this should be the address of X, this should be the address of Y. Okay, that's all what this relocation information is telling you. Okay? Question? Okay. And let's look at the data address, data relocation information. And this goes to data segment, and this goes to BSS segment, which is not shown. Let's look at the data segment. Data segment, first one is goes to the EP. EP should have the address of E. But address of E is unknown. Okay? So they also mark this address is unknown, and they should use absolute address. For all the data address, they should use absolute address, and the address should be the address of variable E, symbol E. And the second data is located at offset 4, which corresponds to 15. So this corresponds to 15, 0, 0, 0, 0, 0, 0, 0, F, which is 15. Okay? So after the compilation, the compiler generates this kind of relocation information, which is just a marking. This address, it either can be a data address or function address. Sometimes it's unknown, right? And they mark using the relocation information. For data address, they use this R386_32 absolute address. For function address, such as calling to A or exit, they use PC relative addressing. It needs to be changed by the linker. Using this relocation information, linker is trying to resolve these symbols in other source files, and they try to find definition. And after they merge together, their absolute address is determined. And then you can change these address. Okay? Okay. Okay, so linker combines this text segment together from m.o and a.o, and they merge together. Okay, so this is m.o and this is a.o. They allocate contiguously in the memory. Okay, and this was actually calling to function A, but which was unknown, so they just put -4 constant, okay, as a placeholder for that address, and they just use PC relative addressing. So, but the address of A is determined. The address of A is here, okay. So you can now, you know now the address. The address should be. They use PC relative addressing. The instruction after, so they should jump to this address, and how many bytes? 1, 2, 3, 4, 5, 6, 7, 8. So using the PC relative addressing, they put +8 in the address. So jump 8 bytes to call function A. Okay, because you now know the address of function A. So this corresponds to 8. 0, 0, 0, 0, 0, 0, 0, 8. Clear? 이렇게 모른 척해. 쉽잖아. 뭐 어려운 거 없지 않나? Okay.
Why they use that address? We was to use that address.
What kind of address are you talking about? This address?
Yes.
Okay, so it's actually same as jump and link in a MIPS instruction set. You are calling to function A, and you use PC relative addressing. PC relative addressing means instead of specifying full 32-bit address, you just specify plus or minus, jump 8 bytes or jump plus 8 bytes or jump backward, plus minus. Okay, and here it's actually jump 8 bytes, which is after this instruction 1, 2, 3, 4, 5, 7. Oh, okay, 1, 2, 3, 4, 5, 6, 7, 8. Then it goes to this address. Okay. Did I answer your question?
I mean, that right side, push one, move well, pull. That they are located
in this address.
yes.
Okay.
Do they choose the address?
Why they linker allocate this main function starting from this address? Is that your question? Usually in x86 architecture, I'm not sure. Okay. Oh, here. Okay. All instructions, okay, all the code starts from this address. This is different from Linux, MIPS address space. This is x86 address space, okay? This is user mode, this is kernel. And all the code starts at here. hexadecimal 08048000. Okay, there are some initialization routines before main. And then, right after this initialization routine, they allocate main function, which is the first function from the user code. Okay? Because there are some initialization code, the address is after this sum address. So 0804 0804 800, and this is actually 0804 800. Instead of 800, this is actually 8530. And initialization routines we'll discuss. These are the initialization routines they put by the Linux before main function. Okay? Other question? Other question? Okay, let me continue. So, this is like opcode, jump and link, and this should be the address, and you are jumping to plus 8 bytes, okay, which is corresponds to this address, which is calling to function A, procedure A, and then this corresponds to push L, and so you after return from function A, you do some stack management, and then you are calling function exit. Okay? Function exit. Exit, this is also same as procedure call. You put this number, this is some negative. In hexadecimal, this should be FFFFFF35. So you are jumping back, going back, because exit is in the initialization routine starting at this address, because exit is somewhere before main, so you are jumping back, and this is some negative number in decimal. Okay, you go to exit, and then no means not do nothing, just for alignment reason, I guess, and then complete. Okay, so this is the main. You call to A, call to exit, and then return. And this is function A. The first instruction of this relocation information is, let's look at here. This is EP. This should be the address of EP, and address of EP was unknown after the compilation, but it's known after linking, after relocation, and it says the address should be 0804A01C. That should be the address of EP. Let's look at the data segment. We have to look at the data segment. So you put data segment from main to here, and from A.O to here. And main, you have only one symbol, which is E. And you have two symbols, EP and X, which is here, right after E. So each symbol occupies 4 bytes because these are all address. Okay? So address of EP, so data segment starts at this address. Okay? And the address of EP should be 0804A01C. Okay? We should put this address in that address that is marked by the location. So 0804A01C, if you hear 0804A01C, which points to EP, the address of EP. Okay? Okay, and then this should be the second relocation information should be the address of X, and the third address should be the address of Y. Okay? So this should be the address of X, and this should be the address of Y. Address of X is here, 0804A020. Okay? And 0804 A020. That is the address of X. And the address of Y is in the BSS section because if you look at Y is uninitialized global variable. And BSS section is not shown here. But there should be the address 0804 A3 D0, which is summed after data segment. Okay?
Y will change it. 2 to 7. Y will change it.
2 to 7? What do you mean by 2 to 7?
552, 557. Y will change it.
Excuse me, I'm not. Which one? This 1, 2, 3. Which one? 3. Okay. Here. What is your question?
줄이 왜 바뀌었어요? 그냥 한 줄에 쓰면 안 되나요? 5개라는 게 복사되는 거.
No, this corresponds to O code and these are the address.
그러니까 한 줄에 쓰면 안 되는 거예요. 왜 2에서 7로 바꿔가지고.
I don't know. Maybe this assembler shows like this fashion. Okay? It may show in this fashion too. It's okay. It doesn't matter. Other question? Can you follow this logic? How do they modify this address? If you understand, you have question? Okay.
For the EP
EP.
on the data,
Or EP on the data section. We'll discuss the data section later. Okay?
but, is that
Okay.
a typo? It should be 1C, not 18.
Which one?
On the red. The red.
0804A018. This one?
Yeah.
Because EP should have the address of E. Address of E is 0804A018, 0804A018. Okay? Other question? Okay, so let me explain this one. Okay. The data segment. So this is from M.O, and these two symbols are from A.O. Okay? And they allocate starting from this address, and E, the initial value is 7. So they put 7. X, initial value is 15, so they put 15. EP, the initial value is the address of E, which is this address. So you should put 0804A018, which corresponds to address of this here. Right? Address of E. That is the initial value for this variable. Okay? Understood? If you can follow the logic, raise your hand. Raise your hand. Raise your hand. No idea, raise your hand. No idea. 그쵸? Raise your hand. There is nothing fancy in linking. This is actually just, it's like linking together. That's all what the linker is doing. Okay? So, in this example, each compiler, by separate compilation, they generate M.O and A.O. Okay? Okay, pay attention. So you generate, the compiler generate M.O and A.O. So M.O, you have text section and the data section. And maybe the BSS section. Here, A.O, there is also text segment, data segment, and BSS segment. Okay? And some of these symbols in text segment or data segment, the symbol has some value, the address. You should put some address. The symbol can be a function address or a variable address. Okay? But the address, sometimes the absolute address is unknown because you don't know how these relocatable object files are linked together by the linker. The order and how many executable file you don't know. Okay? So all these symbol address is unknown, and that's marked by the compiler. You should relocate these address, these symbol address, and so on. The symbol can be a function address or variable address. Okay? So they just mark question mark. Question mark. That's the relocation of information. Question mark for function address. Question mark and use PC relative addressing. That's what that said. Okay? For variable address, question mark and use absolute address. Okay? That's the relocation information. And the linker is very simple. They are trying to merge this data text segment together and data segment together and BSS section together. Okay? They create a single text segment, single data segment, and BSS section, which is actually a placeholder because you don't have to allocate. Okay, let's ignore BSS. You have text segment and data segment. In all instruction set architecture, the address space is determined. So when you create a single text segment start right after initialization routines. Okay? Okay, that's the beginning address of the main function. And then they allocate sequentially. So in this example, after initialization routine, they allocate m.o and a.o. Okay? So all the instructions. And also they have three variables, one from m.o and two from a.o. They move to this data segment, and the beginning address of the data segment is also already determined. You put in those address all the symbols from m.o and a.o, all the definitions. Okay? And then finally, after they merge together, the address of symbols, address of function, or address of variable is determined. Okay? It's definite. You now know the absolute address for each symbol. Okay? Then you can change all this relocation, which is actually a question mark. Okay? That's what this linker is doing. Let me review. So from m.o, what it says is this is question mark. This is actually -4, but you can view them as -4 is just to help the calculation. And -4 is something like a question mark. Question mark use PC relative addressing because this is according to a function. Okay? Function address. This is also question mark according to another function, action. Okay? And that's all. And so 0, here, 0, offset 0 means I don't know. Relatively, from this file, it starts at relative offset 0 because they only know their files. Okay? This is also starting at relative offset 0. All the code, all the data starts at relative offset. But these are question mark you have to change after the linking. And this is also disassembled text segment from a.o here, and you have three address EP, X, and Y. This is unknown. Question mark. Use absolute address. After you determine the address of EP, X, and Y, replace this address. That's what this relocation information is telling you. Okay? And the data segment, they put from so this is data segment for m.o. You have only one variable, one symbol. This is data segment from a.o. You have two symbols, EP and X. And the initial value of EP should be the address of E, which is also unknown. So you mark this using the relocation information. And this is, so you put the number. Okay? So this is after the compilation. And then now linker is trying to combine these two data segments together and these two code segments together and create single text segment and single data segment and mapped to x86 address space, okay, which is here. They put text segment here right after initialization routine. They put data segment here, okay, so they know the starting address. They put one by one, okay, and then they can determine all the address of the symbols, either function address or variable address, okay. So they can modify this question mark using the actual address, okay. So here this is calling to function A and they are using PC relative addressing. So the address of function A starts at this address. And this address from this instruction, this is 8 bytes forward. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So you put 8 because it's based on the address of the current instruction. You jump 8 or jump back. That can be minus. Okay? This is calling to function exit, which is defined in some of the initialization routines, which is allocated before this main. And so you are jumping backward, calling to exit. Okay? So assume that the exit is starting at this should be a negative number, this number backward. Okay? So calling to function A, calling to function exit. And this is the address of EP, X, and Y. Okay? EP, X, and Y, you now know the address of EP, X, and Y because you merge them together, and this is the beginning address of the data segment. Okay? You put first 4 byte E, EP to second 4 byte, and X to third 4 bytes. Okay? Which corresponds to each address. Okay? And E and X, the initial value was 7 and 15. You already initialized. This is the address of E. Okay? The address of E is actually 08, 04, A01A. So you put 08, 04, A01A. Okay? These two addresses, EP, X, and Y, the address of EP is 08, 04, A01C. You put here 08, 04, A01C. This is the address of EP. This should be the address of X. And this is the address of Y, which is actually in BSS section, but I did not show the BSS section in this example. But you can assume that they start at 08, 04, A3, D0. Okay? So you now fix all this question mark. And then you have linked together. That's easy. Okay? Clear? Okay? Still no idea? Okay.
The first 2 bytes are both right?
You mean which 2 byte?
Left. Like 55, 89, E8.
So this corresponds to this push EBP instruction. The first instruction is 1 byte. The second instruction is 2 byte. Okay? This third instruction is 5 bytes and so on. You can speak in Korean. What is your question?
저기 무브 L이라고 A인데 거기
This-
밑에 3개가 쭉 A 무브 L이잖아요.
Yes.
앞에가 다 다른데 그게 왜 그런지.
That's because you don't know the x86. I don't know the x86 either. But in assembly symbolic machine instruction, you can express using move L because move L is quite convenient, but their actual binary opcodes are all different. So here I guess you need for move-L copying to EAX. EAX, you don't have to specify EAX. Maybe EAX might be the default destination register. And this should be the opcode for this move-L to EAX. But other move-L instruction, copying to other register, you have to specify register number also, or something like that. So you need 2 bytes. And the third one is actually moving stack pointer to frame pointer. And they are using this kind of different opcode. Okay? Other question? PC relative addressing. So we have discussed all different addressing modes of MIPS instruction set architecture. Okay? If you remember, PC relative addressing is like, if you have instruction here, BQ, R1, R2, loop. If R1 is equal to R2, you go back to this loop. Okay? So instead of specifying 32-bit address, you can specify minus or plus number and can express. So this means you go back 1, 2, 3, 4, 5 instructions, you can express like this. So PC is actually PC plus this offset, which is minus 4 times 4, something like that. Because each instruction is 4 bytes. So here, it's actually byte. Each instruction is variable. It can be a 1 byte or 2 byte or 4 byte. So you cannot express like this is go back 5 instructions in this example. This is actually go forward 8 bytes. Okay? Because each instruction can be 1 byte or 2 byte. You express by bytes exactly. Is it clear? Okay, that's the PC relative addressing.
Why don't we use this instruction set instead of this x86 instruction set? Because we have learned about it.
Because we are studying 2 different textbooks. Okay? And the previous textbook was from Stanford, and the author of the Stanford, John Hennessy, and actually his graduate students create this company called MIPS, and which was a predecessor for Silicon Graphics computer company, which actually generate workstation for Jurassic Park. But actually Silicon Graphics disappeared because of a bankrupt, but the MIPS sustained, and MIPS is another second popular embedded processor. And this subject is from the second textbook, which is computer systems, and they use basically Unix or Linux, but based on the x86 processor, which is the most popular processor architecture. Okay, so by studying CISC, by studying x86 or MIPS or ARM, you don't have to fear any machine language because they. Yeah, it's confusing, but it's not that much different. Once you know one architecture, you can understand other architecture easily. Okay? Although CISC is quite old instruction set architecture, it's a CISC architecture. We have studied that since 1980s, they don't build CISC style instruction set architecture anymore because of the complexity involved. So this might be 30 years old or more, but still you can understand. It's not that much different. Okay? Other question? So you understand? Okay? Linking is easy, okay? Okay, let's discuss this library. So we have 2 types of libraries, static library or dynamic library. Okay? Static library is actually a set of relocatable object files, a set of or a collection of relocatable object files. Okay? So definition is a package or a set of relocatable related object modules which are relocatable object files, which can be supplied as input to the linker at compile time. So static library is an input to the linker at compile time. And the linker copies only the object modules in the library that are actually referenced by the program. So if you have m.o and a.o, if your programs are standalone, you can link them together and create an executable. But in general, you need some service by the operating system. If you want to manage like I/O device, if you want to do something, sometimes you have to ask operating system for something, right? And so in this case, you have to use some codes that are created by other people, and it's called libraries. It can be system libraries or it can be user level libraries. Okay? So if you have m.o and a.o, you do something, but sometimes you want to print some result, and you have to use printf. If you want to use input, you have to use scanf, which are provided by the NCC standard library. Okay? So it's another user level library, but they are calling operating system service to do some I/O. Okay? So the most famous examples of these libraries are C standard library or NCC master library. So C standard library contains printf, scanf, string copy, and so on. And NCC has some floating point real number, sine, cosine, tangent, these math library modules. So if you have m.o, a.o, you are using printf, you can do like this: gcc compile main.c, and then printf.o scanf.o. You can enumerate all these functions. Okay? But you have to remember. That's complex. Okay? Instead, we do just gcc main.o, and you just call standard C library. And most of functions are provided by this standard C library. Okay? And this is actually, if you do sharp include standard io.h, then it will be automatically generated. Okay? The linker will look at this library. And you can also create a library using AR, archive command, in Linux or Unix. Okay? So, if you want to create a vector library, you compile and generate add vector.c and multi-vector.c, so which means vector addition and vector multiplication. So you have two object files, and you create archive and create live vector.a. This is archive file, which means it's a library. And in this library, it contains these two relocatable object files. Okay? So you can create user level library also. So, using some of them are user level library, some of them are standard C library or system libraries. So, if you, after the compilation, you create main2.o, which is using functions defined in this library or functions defined in some standard system libraries. So, if you only use vector addition, the linker copy only this file. You don't have to copy entire library. You extract only the functions, or only the executable object file that actually has the functions that are referenced by your program, instead of the entire library. So extract add vector.o. So library C.a, they could have lots of object files, but since you use only printf, you can only extract printf.o from the library, and then merge them together and create a single, fully linked executable object file. Okay? Okay, so this is the view of compilation and linking, assuming that you are using only static libraries. Okay? but sometimes you use dynamic libraries too. We'll study what is dynamic library. Okay, let's look at this library a little bit more. So how to package functions commonly used by the programmers. So there are some math functions, I/O functions, memory management, string manipulation, etc. So the options, if you want to package these functions and use them, you can put all these functions in a single source file, and programmers can link this big object file into their programs, right? So there are two options. One is you have printf.o, scanf.o, and all these different files. Instead of different file, you can create a single object file, single source file, and merge all the functions together and create single big object file. Okay? Everything.o. I have everything. Okay? But if you put this all these common use function in a single source file, it's usually space and time inefficient, because each executable object file occupies disk space as well as memory space. If you want to change any function, you need to recompile everything. Okay, it's something like similar to the region that we have studied, separate compilation. You don't want to put everything in everything.o. Then whenever you want to change something, you have to recompile everything. If you want to copy something, you have to copy everything, which will make your program bigger, which will increase your disk space. Okay? Unnecessarily. So option 2 is put each function in a separate source file. Okay? And programmers explicitly link operate binary into their programs. So this is like you have printf.o, scanf.o, and every .o files. And you can specify exactly which one. But which is also somewhat complex to the programmer, because the programmer has to remember what are the object files and so on. Okay? So instead, we use this archive files or libraries. Okay? We merge all related relocatable object file together and create a single library, which is a collection or a set of related object files. Okay? If they are related, you put them in a single library. Okay? Library. And then you enhance linker so that it tries to reserve unreserved external reference by looking for the symbols in these libraries. And then linker will extract only those object files that are actually referenced by your program. You don't have to remember. So you don't have to create big file, or you don't have to know exact file name, but you put them in a library, and the linker will do the job for you. Okay? If you use the library, if there are unreferenced symbols, then it's trying to look up the library, and it will try to extract. And extraction is quite easy. Okay? That's the library. So you create separate locator object file, and you are linking with this static library, standard library, and you extract only those object files. This is set of object file, but you actually extract only a subset that are actually referenced and linked together by the linker, and you should generate executable object file, which contains only code and data for these library that are actually referenced by p dot this your programs. Okay? So this library can actually improve modularity and efficiency by packaging commonly used function in the library. Okay? So static library, for example, the C standard library, there are these kind of separate functions, each are compiled and generated into relocate object files, and using the archive command, they create a set of this object files, which is a library. And using the archiver, you can do incremental update. So if you change only this one, you only need to recompile, and you can change using archive point, you can update only this one. Instead of, you don't have to touch other object files. Okay. So what are the libraries? C.A, standard C library is about 8 megabytes of 900 object files. It has standard input and output, printf, scanf, read, write, or something like that. Okay? And memory allocation, malloc free, signal handling. Signal is something like user level exception handling mechanism. After we'll study what is exception, what is interrupt. If we have time, we'll study signals. If we have time. String handling, date and time, random number generation, and integer math functions are in the standard C library. And C math library is libm.a. It is about 1 megabyte, and there are about 226 object files. It has sine, cosine, tangent, log, logarithmic function, square root, etc. Okay? Using the AR command, you can list all these object files from the library. So this is a command in the Linux or Unix. So using the table -t option, you can specify all these functions from this that are contained in this library. And this is pipe. So the result, the output of this first command goes to the second command. Okay? And the sortage, they sort by alphanumeric order. Okay? If you do the same, and this lists all the functions in the math library and so on. 알겠죠? Let's look at this Linker's algorithm for resolving external reference. There is some issue. So you have m.o and a.o, and you have user level library. You have also system library like C standard library. Okay, and you use GCC and link together. And they are trying to merge text segments together and data segments together. There are all these external reference, and they are trying to identify which symbol is referring. Okay? But they have the linker scan .a files in the command line order. If you find some unresolved reference, you are trying to find this reference from the next .a file or next .a archive file. You are not go back. There is no backtracking. You go forward only. So you have to find all these external reference by a single scan of your argument from the link command. Okay? So they scan .a files and .a files in the command line order. During the scan, they keep a list of current unresolved reference. But this symbol, I don't know where it is. It should be somewhere in the argument afterwards. Okay, they assume. As each new .o or .a file is encountered, they try to resolve each unresolved reference in the list against the symbol in the new .o file or .a file. Okay? If there exists any entries in the unresolved reference at the end of the scan, then it means linking error. Okay, so I have m.o and a.o, and this referred function somewhere here, this referred, okay. But once you scan, you try to resolve reference. If you have printf might be here, so they look at standard C library and they collect standard C the printf.o, extract printf.o. But if you put a library at the beginning, library might be okay. There might be unreserved, there is standalone. But after you scan library, you go to m.o, you use printf. But printf is not defined. You look at a.o, there is no definition of printf. There is generally link error. Even though printf is defined in the first argument, which is standard C library. Okay? So in this example, this is some test object files, and this is library. If you do this kind of linking, the link succeed, because it might call some function in this library, and you can find this function unreserved external reference from this library, and the linking succeeds. But if you reverse this order, okay, in this case, it tells that in a function main is trying to look at library function, but library function is defined in this archive. But since linking is scanning this argument in this command line order, they do not go back. They do not look back. So even though you find unreserved reference here, which is here, they generate linking errors. 쉬운 건데 이렇게 어렵게 내가 설명이 되나? 무슨 말인지 알겠나? 응? 나 지금 목이 자꾸 잠겨가지고 약간 어려운데. And this is just to simplify the linker. Okay? So if the linker is smart, if you have unreserved reference in your object files, and as long as your arguments, which can be an object file or archive file, supplies that definition of that function or whatever, then it should be fine. If the linker is smart, right? So intuitively you think that as long as your reference is defined somewhere, there is a definition and reference. There can be a function definition or variable definition. There is also a function reference or variable reference. As long as you can find that definition from your object files or archive files, the linker, if they examine all together, then they can find the definition and they can resolve all these external reference. Okay? Okay? But to do that, sometimes the linker should go back forward or backward to find out all these definitions. To simplify the linker, linker is scanning the other file and the .a file in the command line order. They do not go back. So if you find some unreserved reference, you should find from there or afterwards definitions. Okay? So if you put this order, you put your object file and then library, and the object file is referring to a function in the library, then even though you are calling to a function, you can do the linking successfully because you find some unreserved reference, but you find that reference in the argument afterward, okay, from the library. But if you reverse this order, because this linker is scanning only a unidirectional way, sometimes they can, even though in live test.o is calling function, this function which is defined in archive. Okay? So in this case, it do not go back. It do not look back. So it cannot do the linking because they look at this argument in the command line order. That's what I'm saying. Okay? So there is some restriction to simplify the linker. Okay? 알겠죠? Understood? 어려운 건 없어요, 여기서. So after the linking, so after compilation, after linking, you now create executable object files, which means it can be copied into the memory and it can be run. Okay, this is actual executable file. The format of executable file is, for Linux or Unix, you use the same format, but there is some difference in the details. It's similar to the format of relocatable object file, except in the following way, it's different from relocatable object file. In an executable object file, the ELF header includes programmed entry point. Entry point is the address of the first instruction. So it specifies the first instruction is here. Okay? And init section defines a small function called underscore init that will be called by the program's initialization code. So actually, before main, there are some initialization routines which are defined in the init segment. And since you have done relocation, you don't need relocation information. So in the executable object file, in ELF binaries, there are no relocation information. Okay? And you need to have the segment header information, which actually describe the mapping between the segment in the executable object file and the memory segment in the virtual address space, so that the loader can copy into the memory space correctly. So, and you have also read-write executable permission information in this header. So this is ELF file. This segment header is only for executable because this is for the mapping between executable file and the memory segment in the address space. And this is actually the code segment. There are some initialization routines and the text segment, and there is some read-only data, which is a read-only segment, code segment, and there are data segment and BSS segment. And this information is not loaded into memory by the loader. Okay? And there is no relocation information because this is executable file. Okay, so there is no relocation information. So from executable object file, so this information is you don't need, right? By the loader, this is actually copied into memory, virtual address space. This is copied into memory, and BSS section is created by the loader dynamically, because this is all on initialized variable, so it will be maybe initialized by default to zeros and created at runtime. And these are shared library, shared object files, which are linked dynamically at runtime. Okay? By the dynamic linker. 오케이, 오늘 여기까지 합시다.